Okay, so this is the last topic for this first part of this lecture, transfer batching. And as I mentioned, there's two type of batch that we're discussing. First one is the process batch, and the second one is the transfer batch. So today we're going to focus on the transfer um, component. So move batching law says that cycle times over a segment of a routing are roughly proportional to the transfer batch size used over that segment. And this is provided that there's no waiting for the convenience of the device. Okay, so the insights that we can get from this law is that there's a trade-off between two things here. So the basic batching trade-off is going to be between the WIP versus move frequency. And the queuing for convenience device can offset the cycle time reduction from reduced move of the batch size. So the move batching is related to the material handling and also the layout decisions. And the layout decisions basically is the configuration of your machine. So how many machines you're going to be having, if they're going to be sequenced or they're going to be working in parallel. So that's what we're referring to as layout decisions. And on the next slide, I have an example of a move batching. So here we have two machines in series. The first machine received individual parts at a rate of RA, so this is the arrival rate, with a coefficient of variance of the arrival process of 1, and put out batches of size K. So we are receiving a number of units coming into the first machine, and then we are putting them together to move them to the next machine in a batch of size K. The first machine has a mean process time of 1 for one part, and a coefficient of variance also of 1. So we are keeping things very simple. The second machine received batches of K because they're coming from here. They're coming from the first station, so we are putting them together. We are sending them to the next machine and put out individual parts. So the only batching that is happening in this system is between station 1 and station 2. So the question is, how does the cycle time depends on this size? I mean, it depends on how many units you have in that batch that is moving from one station to the other. So, so we can use some of the equations that we learned earlier in this course to come up with an expression that can give us some intuition about how would that affect our cycle time. So the average time before batching is going to be equal to the coefficient of the square coefficient of variance of the arrival process plus the square coefficient of the effective processing time divided by 2 multiplied by the utilization rate times the expected time plus the effective time of that processing on the machine. So this is the regular BUT equation that we learned before. Now we can add to that time the average time for forming the batch. And that's going to be given by this equation right here, which is basically taking into consideration the size of the batch and also the arrival process or the rate of arrivals. And that expression is going to be equal to here. So the first part, weight K minus 1 times 1 over RA, and the last part doesn't weight. So in average, we can get this number. And then the average time spent at the first station is going to be a combination of the two. So it's going to be this BUT part of the equation plus the time regarding to forming the batch. And that's going to be the total time spent at that first station. So the output of the first station includes the time between output of individual parts into the batch, and that's TA. Time between output of batches of site K, that's going to be K times TA. And then the variance of inter-output times of parts, which is the coefficient or the square coefficient of variance of the departures of that first station times the time of arrival squared. Okay, so we can get that coefficient of variation, or the square coefficient of variation of the departure process using this expression. Okay, so the variance of the batches of size K is going to be K times this coefficient, square coefficient of variance of the departure process times the square of the time of the arrival. So because departures are independent, we can add the variances of those items, and the square coefficient of variance of batch arrivals to station 2, then we can get that coefficient of variance of the arrival of the batches by simplifying into this equation, which is basically the square coefficient of variance of the departure process that we define here divided by the number of units in your batch. So using that information, then we can compute the time at the second station. So the time to process a batch of size K is going to be equal to the number of items in that batch times the effective time of that second station. The variance of time to process a batch of size K is going to be equal to the square coefficient of variance of the effective time multiplied by the size of the batch times the effective time of the square effective time of that processing on that second station. So the square coefficient of variance for a batch of size K is, we already defined that, and the mean time spent in the partial batch of size K is here. So the third part doesn't weight, that part weights K minus 1 times the effective time of the second station, so we can get the average of that as well. So finally, the average time spent at the second station, again, is going to be the combination of the time spent at the station plus the time of that departure process. So the VUT equation to compute the Q time of batches is going to be equal to that cycle time of 2 with no batching plus this expression that we defined right here, which is the mean time spent in partial batch of size K. So as you can see, we are basically trying to use all the things that we have learned so far to come up with some new expressions to analyze specific systems. So in this case, these equations are going to apply to the system that is defined as this one. Okay, so this is probably not your typical system, but if you have a system like this in which you have an arrival process, you're forming a batch, and then you're moving that batch to the second station, and then you're releasing parts independently, then you can come up with a set of expressions that can define the cycle time for that specific process. Okay, this equation would not apply, for example, to a system in which there's no batches happening in between, which is the type of system that we were talking before this one. But that's the idea. So the total cycle time for the system then is going to be the cycle time for not batching plus K minus 1 divided by 2U, the utilization of 1, times T multiplied by 1 plus this K minus 1 divided by 2 times the time or the effective time of the second station. Okay, so the inflation factor due to moving those parts into a batch is basically this part of the equation. Okay, so the inside cycle time increases with the size of the batch, right? Because if you see this part of the equation, the largest is K value, the largest that inflation factor. The implied inflation term does not involve the coefficient of variances, so there's no CVs in here. There's only the size of the batch, the effective time at the stations, and the utilization of the first machine. So congestion from batching is more back control than randomness. So it's not necessarily the variability of the stations in this particular system, but it's actually affecting that is, are you deciding the right size for your batch to transfer them to the next stage. Okay, and that concludes this part of the lecture. Now we are going to transition to the second part of this topic, which is on your second set of slides, or 3 part 2. So let me